Have you ever looked at the night sky and wondered how planets move in their orbits? Or maybe you've marveled at the intricate design of a flower, curious about the patterns nature creates? These questions, along with countless others, can be explored through the fascinating world of calculus. Now, before you run for the hills thinking calculus is some scary mystical math only geniuses can understand, let me assure you, it's not. Calculus is, at its heart, a way to study change. Not just any kind of change, but the kind that's happening all around us, all the time. Think about a car accelerating, a plant growing, or the temperature rising throughout the day. These are all examples of change, and calculus gives us the tools to analyze them in a precise and powerful way. For centuries, calculus has been the secret language of scientists, engineers, and mathematicians. It's helped us build bridges, design airplanes, understand the human body, and even land on the moon. But for too long, calculus has been shrouded in an aura of intimidation, making people believe it's beyond their grasp. Here's the truth. Calculus is for everyone. Just like learning a new language or playing a musical instrument, it requires patience, practice, and a willingness to explore. And the reward? A whole new way of seeing and understanding the world around us. This guide is your invitation to demystify calculus, to break it down into bite-sized pieces that anyone can digest. We'll use everyday language, relatable examples, and even a little bit of humor to make the journey enjoyable. Think of it like this. We're about to embark on an adventure, and calculus is the map that will lead us to some truly amazing discoveries. Forget those complicated formulas and abstract theorems that make your head spin. We'll focus on the core concepts, using visual aids, step-by-step explanations, and real-world applications to make sure everything clicks. So, whether you're a student, a professional, or just someone with a curious mind, get ready to unlock the power of calculus. You might be surprised at how much you already understand intuitively, and how empowering it can be to grasp these fundamental principles. To truly appreciate the magic of calculus, we need to take a quick trip back in time. Imagine yourself in the 17th century, a time when scientists like Isaac Newton and Gottfried Leibniz were grappling with some of the biggest questions about the universe. They wanted to understand how planets moved, how objects fell to the earth, and how to describe the continuous motion of the natural world. These brilliant minds realized that existing mathematical tools were simply not enough. They needed a new language, a new set of rules, to capture the essence of change and motion. And thus, calculus was born. Think of it as a revolution in thought, a way to express the complex dance of the universe in elegant equations. Newton, working on the laws of gravity and motion, and Leibniz exploring patterns and infinitesimal changes, independently developed the key principles of calculus. They discovered that by breaking down complex problems into infinitely small parts, they could analyze change with incredible precision. This revolutionary idea of understanding the whole by examining its tiniest pieces is at the very core of calculus. It's like looking at a masterpiece painting up close, noticing the individual brushstrokes that, when combined, create a breathtaking work of art. Fast forward to today, and calculus is everywhere. It's the driving force behind countless technological advancements, from the smartphones in our pockets to the rockets launching into space. Engineers use calculus to design bridges that can withstand immense weight, airplanes that soar through the sky, and cars that are both safe and fuel efficient. But calculus isn't just confined to labs and research facilities. It's all around us in our everyday lives, even if we don't always realize it. When you watch a basketball player sink a perfect three-pointer, calculus helps describe the arc of the ball. When you listen to music on your phone, calculus is behind the algorithms that compress and transmit those sound waves. Take a roller coaster, for example. The exhilarating twists, turns, and drops are all carefully calculated using, you guessed it, calculus. Engineers use calculus to determine the perfect slope of each curve, the speed of the cars, and the forces exerted on the riders, ensuring a thrilling yet safe experience. From the smallest microchip to the vastness of space exploration, calculus is the silent architect shaping our world. And the best part? By understanding its fundamental principles, you too can gain a deeper appreciation for the intricate workings of our universe. You don't have to be a rocket scientist to see calculus in action. Nature is a masterclass. Every leaf, snowflake, and ripple shows calculus at work. The hexagonal honeycomb, it's nature's way of optimizing space and material. Even a fountain's arc is shaped by calculus. By seeing the world through calculus, we unlock a deeper appreciation for our planet. As we embark on this journey to demystify calculus, remember that every great achievement begins with a single step. Our goal is to break down this seemingly daunting subject into manageable chunks, using clear language, relatable examples, and, hey, even a touch of humor along the way. We'll explore the two main branches of calculus: differential calculus, which deals with rates of change, and integral calculus, which focuses on accumulation. Don't let these terms intimidate you. We'll use everyday analogies and visual aids to make sure these concepts really click. Think of this guide as your friendly companion on this exciting adventure. We'll provide you with all the tools and support you need to grasp the fundamentals of calculus, build your confidence, and even have some fun along the way. So buckle up and get ready to explore the fascinating world of calculus. Trust us, it's much easier and honestly, much more exciting than you might think. Imagine a river flowing downstream, constantly changing direction and speed. Now imagine trying to describe that river's journey using only words. You might talk about its twists and turns, its rapids and calm stretches, but capturing the full essence of its dynamic flow would be nearly impossible. That's where calculus comes in. Calculus is the mathematics of change, a way to describe and analyze the continuous flow of the world around us. It goes beyond static snapshots and delves into the dynamic relationships between quantities, like how speed changes over time or how a curve bends at a specific point. Think about a car accelerating from a standstill. At any given moment, we can measure its speed, but calculus allows us to understand how that speed changes from one instant to the next. It provides us with the tools to calculate the car's acceleration, its rate of change of speed, and predict its future position based on its current trajectory. This ability to quantify and analyze change is what makes calculus so powerful. It allows us to move beyond simple descriptions and delve into the underlying mechanisms that govern our universe, from the motion of celestial bodies to the growth of populations. Calculus is truly the language of motion, of transformation, of the ever-evolving tapestry of our world. For centuries, mathematicians struggled to describe motion and change in a precise and rigorous way. They could calculate the speed of an object moving at a constant speed, but what about objects that were constantly accelerating, like a ball rolling down a hill or a rocket launching into space? Calculus provided the breakthrough they were looking for. By introducing the concept of infinitesimal change, calculus allowed mathematicians to break down complex motions into infinitely small intervals. Imagine, just for a moment, zooming in on a curve until it appears almost straight, capturing the instantaneous rate of change at that specific point. This concept of the derivative, the rate of change at a single point, is one of the cornerstones of calculus. It allows us to calculate the slope of a curve at any given point, representing the instantaneous rate of change of one variable with respect to another. For example, the derivative of a car's position, with respect to time, is its velocity, which is its instantaneous speed at that moment. Similarly, the integral, the other fundamental concept in calculus, allows us to calculate the accumulated effective change over time. It's like summing up all those infinitesimal changes to find the total area under a curve, representing the total accumulation of a quantity over a given interval. Imagine measuring a rugged island's coastline. A long ruler misses the details, while a shorter one captures more but still approximates. Calculus lets us zoom in infinitely, measuring even the most complex shapes with perfect accuracy. By breaking things into tiny pieces, we reveal hidden patterns and understand change on an infinitesimal scale. Infinity has fascinated thinkers for centuries. Calculus harnesses this idea to understand continuous change. At its core is the limit, approaching a value without ever reaching it. The derivative measures instantaneous change, while the integral accumulates change over time, both powered by the concept of limits. Derivatives and integrals are like two sides of the same coin, separate yet deeply connected. The fundamental theorem of calculus is the bridge linking them, showing they are inverse operations. It tells us that knowing a rate of change lets us find total change, and vice versa. This elegant connection reveals the hidden harmony in mathematics. Change is at the heart of calculus, but how do we measure it? That's where derivatives step in. Like clues in a mystery, derivatives reveal how things change at any moment. It's like checking a speedometer, showing speed right now, not before or after. Whether it's a plant's growth or a car's velocity, derivatives capture these fleeting moments of change. Imagine you're driving down the highway, your foot pressing on the gas pedal. Your car's speed isn't constant, it's constantly changing as you accelerate and decelerate. The speedometer, that trusty gauge on your dashboard, is like a real-time derivative calculator showing you the instantaneous rate of change of your car's position, which we call velocity. Now imagine you could record your car's speed at every single moment during your trip. You'd end up with a long list of speed readings, each one representing your velocity at a specific point in time. This list would give you a pretty good idea of how your speed changed throughout your journey. That's essentially what a derivative does. It captures those instantaneous rates of change, those speedometer readings, for any function we can imagine. Whether it's the growth of a population, the spread of a virus, or the cooling of a cup of coffee, derivatives allow us to track those changes with incredible accuracy. So, the next time you glance at your speedometer, remember that you're witnessing the power of derivatives in action. They're the mathematical engines that allow us to understand and analyze change in a world that's constantly in motion. Graphs are like visual storytellers, allowing us to see patterns and relationships that might be hidden in tables of numbers. When it comes to derivatives, graphs become even more powerful, providing us with a way to actually see the instantaneous rate of change at any point on a curve. Imagine a roller coaster track represented by a curved line on a graph. The steeper the curve, the faster the roller coaster is moving at that point. The derivative at any given point on that curve is simply the slope of the line that's tangent to the curve at that point. A tangent line is like a ruler that just grazes the curve at a single point, capturing its direction and steepness at that precise moment. The slope of that tangent line represents the instantaneous rate of change of the function at that point, which is exactly what the derivative tells us. So, when we talk about finding the derivative of a function, we're essentially finding a way to calculate the slope of the tangent line at any point on its graph. This visual representation of the derivative helps us understand how the function is changing at every single point, revealing its hidden dynamics and patterns. Why is it so important to be able to calculate instantaneous rates of change? Because the world is rarely static. Things are constantly in motion, constantly transforming, and understanding those changes is crucial in countless fields, from physics to economics, from engineering to medicine. Imagine trying to predict the trajectory of a rocket launching into space. Knowing its average speed isn't enough. We need to know its instantaneous velocity at every moment to ensure it stays on course and reaches its destination safely. Or consider a doctor monitoring a patient's heart rate. The average heart rate over an hour doesn't tell the whole story. The doctor needs to see the instantaneous changes in heart rate, those subtle fluctuations that could indicate a medical issue. Derivatives give us the power to unlock these instantaneous rates of change, to see beyond the averages and delve into the dynamic nature of the world around us. They allow us to analyze and predict change with a level of precision that was unimaginable before the invention of calculus. To truly grasp the concept of the derivative, it helps to understand how it emerges from the idea of average rate of change. Imagine you're on a road trip, and you want to know your average speed over the entire journey. You'd simply divide the total distance traveled by the total time taken. But what if you want to know your speed at a specific moment during the trip? You could look at your speedometer, of course, but let's say you only have a stopwatch and a map. You could choose 2 points on your route that are very close together, measure the distance between them, and divide by the time it took you to travel that short distance. This would give you your average speed over that tiny interval, which would be a pretty good approximation of your instantaneous speed at that moment. The shorter the distance between those 2 points, the more accurate your approximation would be. The derivative takes this idea to the extreme, shrinking that interval down to an infinitesimally small size. It's like calculating your average speed over a distance so small that it's practically zero, giving you the instantaneous rate of change at that precise moment. One of the most powerful aspects of the derivative is that it's not just a single number, but, a function itself. Just as a function can describe a relationship between two variables, the derivative of that function can describe how that relationship is changing at every single point. Think about a curve on a graph representing the growth of a tree over time. The derivative of that curve would be another curve representing the tree's growth rate at every moment in time. This derivative function would tell us not only how fast the tree is growing at any given moment, but also whether its growth is speeding up, slowing down, or remaining constant. This ability to describe change at every point is what makes the derivative such a versatile tool. It allows us to analyze the behavior of functions in detail, to identify critical points where the function is changing most rapidly or slowly, and to gain a deeper understanding of the underlying dynamics of the system being modeled. Finding derivatives from first principles using the limit definition can be a bit like trying to navigate a maze blindfolded. It's possible, but it can be tedious and time-consuming. Fortunately, mathematicians have developed a set of rules like shortcuts through the maze that make finding derivatives much easier. These rules, known as differentiation rules, are like mathematical recipes that tell us how to find the derivative of a function based on its form. For example, the power rule tells us that the derivative of x to the n is n times x to the power of n minus 1. So the derivative of x squared is 2x, the derivative of x cubed is 3x squared, and so on. Other rules like the sum rule, the product rule, and the quotient rule allow us to find the derivatives of more complex functions by breaking them down into simpler parts. These rules are essential tools for anyone working with calculus, allowing us to find derivatives quickly and efficiently without having to go through the entire limit process every time. Imagine a set of Russian nesting dolls, each one tucked inside a larger one. Composite functions are a bit like that, with one function nested inside another. For example, the function f of g of x is a composite function, where the output of the inner function, g of x, becomes the input of the outer function, f of x. Finding the derivative of a composite function requires a special tool, the chain rule. The chain rule tells us that the derivative of a composite function is equal to the product of the derivative of the outer function evaluated at the inner function and the derivative of the inner function. In simpler terms, it's like peeling back the layers of the nesting dolls, taking the derivative of each one in turn. The chain rule is essential for finding the derivatives of many common functions, especially those involving trigonometric functions, exponential functions, and logarithms. Just as we can find the derivative of a function, we can also find the derivative of that derivative, and the derivative of that derivative, and so on. These are called higher-order derivatives, and they allow us to delve even deeper into the dynamics of change. The second derivative, for example, tells us how the rate of change itself is changing. Imagine a car accelerating. The first derivative, its velocity, tells us how fast it's going. The second derivative, its acceleration, tells us how quickly its velocity is changing, whether it's speeding up, slowing down, or remaining constant. Higher-order derivatives might seem a bit abstract, but they have important applications in physics, engineering, and other fields. For example, the second derivative is crucial for understanding concepts like acceleration, curvature, and the behavior of oscillating systems. Derivatives might seem like abstract mathematical concepts, but they have countless applications in the real world, helping us understand and solve problems in fields as diverse as physics, engineering, economics, and medicine. In physics, derivatives are essential for describing motion, force, and energy. They allow us to calculate the velocity and acceleration of objects, to analyze the forces acting on them, and to understand the relationship between energy and work. In economics, derivatives are used to analyze markets, model supply and demand, and optimize production and pricing strategies. They allow economists to understand how changes in one variable, like interest rates or consumer spending, can ripple through the economy and affect other variables. From designing safer cars to developing new medical treatments, derivatives are essential tools for understanding and shaping the world around us. They are the mathematical engines that power countless technological advancements and scientific discoveries. One of the most powerful applications of derivatives is in optimization, the art of finding the best possible solution to a problem. Whether it's maximizing profits, minimizing costs, or designing the most efficient structure, derivatives provide us with the tools to find those optimal solutions. Imagine you're a business owner trying to determine the price of a product that will maximize your profits. You could use trial and error, but derivatives offer a more systematic approach. By finding the derivative of your profit function and setting it equal to zero, you can identify the critical points where your profit is either maximized or minimized. This concept of finding critical points using derivatives is crucial in many fields, from engineering to finance. It allows us to optimize designs, allocate resources efficiently, and make informed decisions based on mathematical analysis. As we've explored in this act, derivatives are far more than just abstract mathematical concepts. They are powerful tools that allow us to unlock the secrets of change, to see beyond the static and delve into the dynamic nature of our world. From the graceful arc of a ball in flight to the complex fluctuations of the stock market, derivatives help us make sense of the constant motion and transformation that surrounds us. They provide us with the language to describe change, the tools to analyze it, and the power to predict and even shape its course. As you continue your journey into the world of calculus, remember that derivatives are not just formulas to memorize, but keys to understanding. Embrace the power they offer, and you'll unlock a deeper appreciation for the intricate dance of change that shapes our universe. While derivatives unveil the secrets of instantaneous change, integrals take us on a different journey, one that explores the accumulated effects of those changes over time. Imagine a detective meticulously gathering evidence piece by piece to reconstruct a complete narrative. Integrals are like those pieces of evidence, allowing us to sum up infinitesimal changes and reveal the bigger picture of accumulation. Think about a steady drizzle of rain falling into a bucket. Each raindrop adds a tiny amount of water, and over time, those minuscule contributions accumulate into a significant volume. Integrals provide us with the mathematical tools to measure that accumulation, to calculate the total amount of water collected in the bucket based on the rate of rainfall over time. But integrals go beyond simple accumulation. They allow us to calculate the area under a curve, representing the total accumulation of a quantity represented by that curve over a specific interval. This concept has far-reaching applications, from determining the work done by a force to calculating the total distance traveled by a moving object. Integrals are the mathematical detectives that piece together the story of accumulation, revealing the hidden connections between infinitesimal changes and their cumulative effects over time. Imagine trying to measure the volume of water flowing in a river. You could try to count every single water molecule, but that would be an impossible task. Instead, we can use the concept of summation, dividing the river into smaller sections and measuring the flow rate in each section. Integrals work in a similar way, but instead of dividing the problem into a finite number of sections, we divide it into an infinite number of infinitesimally small sections. It's like adding up an infinite number of infinitely small raindrops to find the total volume of water in a rainstorm. This process of summing up an infinite number of infinitesimal quantities is at the heart of integration. By breaking down a complex problem into infinitely small pieces, we can analyze it with incredible precision, capturing the subtle nuances of accumulation that would otherwise be lost. From calculating the area of irregular shapes to determining the work done by a variable force, integrals provide us with the tools to tackle problems that involve accumulation and summation, revealing the hidden order in seemingly chaotic systems. Section 3, Area under the curve, visualizing integrals as geometric shapes. Graphs are, just really powerful tools for visualizing mathematical concepts, and integrals are no exception. When we talk about finding the integral of a function, we're essentially talking about finding the area bounded by the curve of that function, the x-axis, and two vertical lines representing the limits of integration. Imagine a curve on a graph representing the speed of a car over time. The area under that curve, bounded by the curve itself, the time axis, and two specific times, would represent the total distance traveled by the car during that time interval. This geometric interpretation of the integral is incredibly useful for understanding its meaning and applications. It allows us to see the integral as a tangible quantity, something we can actually visualize and measure, rather than just an abstract mathematical concept. From calculating the area of a circle to determining the volume of a solid of revolution, integrals provide us with the tools to measure and understand the geometry of change, connecting the abstract world of calculus to the tangible world of shapes and spaces. Section 4. The integral as antiderivative, reversing the flow of change. Imagine watching a film in reverse. Actions are undone, effects precede causes, and the flow of time seems to run backward. That's essentially what we're doing when we find the antiderivative of a function. We're reversing the process of differentiation, retracing the steps that led to the derivative in the first place. The antiderivative, also known as the indefinite integral, is a function whose derivative is equal to the original function. It's kind of like finding the original recipe after tasting a delicious dish, or reconstructing a broken vase from its scattered shards. This concept of reversing differentiation is fundamental to understanding integrals. It allows us to find functions that describe quantities based on their rates of change, to reconstruct the whole from its parts, and to move from the instantaneous to the accumulated. The antiderivative is the key to unlocking the secrets of integration, providing us with the tools to reverse the flow of change and reveal the hidden connections between rates of change and their accumulated effects. Section 5, the Fundamental Theorem, Part 2, Connecting Integrals and Derivatives. In Act 2 we explored the first part of the fundamental theorem of calculus, which revealed the profound connection between derivatives and integrals as inverse operations. Now let's delve into the second part of this theorem, which provides us with a powerful tool for evaluating definite integrals using antiderivatives. The second part of the fundamental theorem of calculus states that to find the definite integral of a function over a specific interval, we can simply find the antiderivative of that function, evaluated at the upper and lower limits of integration, and subtract the two values. This might sound a bit abstract, but it's actually a remarkably elegant and efficient way to calculate definite integrals. Instead of having to go through the tedious process of summing up an infinite number of infinitesimal quantities, we can simply find the antiderivative and plug in the limits of integration. The fundamental theorem of calculus is a testament to the beauty and interconnectedness of mathematics, revealing the hidden harmony between differentiation and integration and providing us with powerful tools for understanding and analyzing change. While indefinite integrals give us general solutions to antiderivatives, definite integrals allow us to focus on specific intervals, measuring the accumulated effect of change over those specific ranges. Imagine you're tracking the growth of a plant over a month. The indefinite integral of its growth rate function would give you a general formula for its height at any given time. But what if you're only interested in how much it grew during the second week? That's where definite integrals come in. A definite integral represents the area under a curve between two specific points, those points being the limits of integration. In our plant example, the definite integral of the growth rate function between the start and end of the second week would give you the exact amount the plant grew during that period. Definite integrals are essential for quantifying change over specific intervals, whether it's calculating the total distance traveled by a moving object between 2 points in time, or determining the total work done by a variable force over a specific distance. They give us the precision to zoom in on specific segments of a function and measure the accumulated effects of change within those boundaries. Imagine you're trying to find a missing piece of a puzzle, but you don't have the complete picture to guide you. That's the challenge of finding indefinite integrals. Unlike definite integrals, which focus on specific intervals, indefinite integrals give us general solutions to antiderivatives, representing a family of functions that all share the same derivative. Think about the function f of x equals 2x. Its derivative is simply f prime of x equals 2. But what about its antiderivative? Well, there are actually infinitely many functions that have a derivative of 2. For example, f of x equals x squared, f of x equals x squared plus 1, and f of x equals x squared minus 5 all have the same derivative. That's why when we find the indefinite integral of a function, we always add a constant of integration, usually denoted by c. This constant represents that unknown shift or vertical translation that could be applied to the antiderivative without changing its derivative. Indefinite integrals provide us with a powerful tool for finding general solutions to antiderivatives, allowing us to explore the family of functions that share a common rate of change. They are the building blocks for solving differential equations, modeling dynamic systems, and understanding the fundamental relationships between functions and their rates of change. Finding antiderivatives is a bit like solving a puzzle. And just like with puzzles, there are techniques and strategies that can make the process easier. While some integrals can be solved using simple rules, others require more advanced techniques like substitution, integration by parts, and trigonometric substitutions. Substitution, for example, is like changing the language of an integral, making it easier to understand and solve. It involves substituting a new variable for part of the integrand, simplifying the expression and making it easier to integrate. Integration by parts, on the other hand, is like a mathematical tango where we carefully choose two dancers, parts of the integrand, and apply a specific formula to integrate their product. This technique is particularly useful for integrals involving products of functions, such as the product of a polynomial and an exponential function. Mastering these integration techniques is essential for anyone working with calculus, allowing us to tackle a wide range of integrals and unlock the secrets of accumulation in diverse fields, from physics to economics, from engineering to computer science. Section 9. Substitution, simplifying integrals by changing variables. Imagine trying to solve a jigsaw puzzle with pieces that are all the same color and shape. It would be incredibly difficult, if not impossible. Substitution in integration is like finding a way to recolor and reshape those puzzle pieces, making it easier to see how they fit together. This technique involves choosing a new variable, often denoted by u, to represent part of the integrand. This substitution, if chosen wisely, can simplify the integral significantly, turning a complex expression into something more manageable. The key to successful substitution lies in choosing the right u. It's like finding the right key to unlock a door. Once you've made the substitution, you also need to adjust the limits of integration accordingly, ensuring that the new integral represents the same area as the original one. Substitution is a powerful tool for simplifying integrals, allowing us to tackle more complex problems and expand our repertoire of integration techniques. It's like having a secret weapon in our mathematical arsenal, ready to be deployed when faced with a particularly challenging integral. Section 10. Integration by parts. Tackling products of functions. Integration by parts is like a mathematical dance, a carefully choreographed routine for integrating products of functions. Just as a dance requires two partners moving in sync, integration by parts requires us to choose two parts of the integrand and apply a specific formula to integrate their product. The formula for integration by parts is derived from the product rule of differentiation, but instead of finding the derivative of a product, we're finding the integral. The key to success lies in choosing the right u, the part we differentiate, and dv, the part we integrate. This technique is particularly useful for integrals involving products of different types of functions, such as the product of a polynomial and an exponential function, or the product of a trigonometric function and a logarithmic function. It's like having a special tool for disassembling a complex structure into smaller, more manageable components. Integration by parts, combined with other integration techniques, expands our ability to tackle a wide range of integrals, revealing the hidden patterns and relationships within complex functions and their accumulated effects. Section 11, Integrals in Action, from calculating areas to predicting rocket trajectories. Integrals might seem like abstract mathematical concepts, but they have countless applications in the real world, helping us solve problems in fields as diverse as physics, engineering, economics, and medicine. In physics, integrals are essential for calculating work, energy, and momentum. They allow us to determine the work done by a variable force, the energy stored in a spring, and the momentum of a moving object. In engineering, integrals are used to calculate areas, volumes, and centroids. They allow us to determine the area of a curved surface, the volume of a solid of revolution, and the center of mass of an irregularly shaped object. From predicting the spread of diseases to modeling the behavior of financial markets, integrals provide us with the tools to understand and analyze the accumulated effects of change in complex systems. They are the mathematical engines that power countless technological advancements and scientific discoveries. As we've explored in this act, integrals are far more than just mathematical formulas. They're actually powerful tools that allow us to look beyond the instantaneous and delve into the accumulated effects of change over time. From the gentle accumulation of raindrops in a bucket, to the complex trajectories of rockets soaring through space, integrals provide us with a framework for understanding how infinitesimal changes can lead to significant outcomes. They give us the language to describe accumulation, the tools to analyze it, and honestly, the power to predict and even shape its course. As you continue your journey into the world of calculus, remember that integrals are not just symbols to manipulate, but keys to understanding the dynamic interplay between change and its cumulative impact on our world. Embrace the power of integration and you'll unlock a deeper appreciation for the intricate tapestry of cause and effect that shapes our universe. Hold on tight as we ride the Calculus Express, where thrills are designed and safety is paramount. Every loop, drop, and curve is carefully calculated using calculus to deliver a thrilling yet safe experience. As you plunge down the first drop, calculus ensures the forces you feel stay within safe limits. So next time you buckle up, remember, calculus is behind every thrill. Step into the grand theater of nature, where calculus takes center stage not on a chalkboard, but in the intricate designs and efficient processes of the living world. From the spiraling patterns of seashells to the branching networks of trees, nature showcases the elegance and practicality of calculus in countless ways. Consider the humble honeycomb, a testament to nature's ingenuity. Bees, those master architects, construct their honeycombs with hexagonal cells, a shape that maximizes storage space while minimizing the amount of wax needed. This remarkable feat of optimization is a testament to nature's inherent understanding of calculus. Or take a look at the graceful arc of a bird in flight. Calculus helps us understand how birds adjust their wingspan and angle of attack to minimize air resistance and maximize lift, allowing them to soar effortlessly through the sky. From the tiniest insects to the largest mammals, nature utilizes the principles of calculus to optimize movement, conserve energy, and thrive in diverse environments. Nature's calculus is subtle yet profound, a testament to the interconnectedness of mathematics and the natural world. By observing and understanding these natural phenomena, we gain a deeper appreciation for the elegance and efficiency that calculus brings to the grand design of life. Section 3, the rhythm of the universe, calculus, and the laws of motion. So, look up at the night sky, a canvas of twinkling stars and distant galaxies, and you're witnessing the grand ballet of the cosmos, a celestial dance choreographed by the laws of motion and illuminated by the language of calculus. From the orbits of planets to the trajectories of comets, calculus provides us with the tools to understand and predict the movements of celestial bodies. Now, imagine yourself transported back to the time of Isaac Newton, who revolutionized our understanding of gravity and motion. Newton's laws of motion, expressed in the elegant language of calculus, describe the relationship between force, mass, and acceleration, laying the foundation for classical physics. Calculus allows us to calculate the gravitational force between celestial bodies, to determine their orbits with remarkable accuracy, and to predict their positions far into the future. It's like having a cosmic GPS, guiding us through the vast expanse of space and time. From launching satellites into orbit to planning interplanetary missions, calculus is an indispensable tool for exploring the cosmos and unraveling the mysteries of the universe. It's the language of the stars, a testament to the power of mathematics to describe the grandest scales of nature. Section 4. Calculus and Technology. From smartphones to space exploration. Our world is increasingly driven by technology, and behind the scenes, quietly powering our digital lives, is the often unseen force of calculus. From the smartphones in our pockets to the GPS systems guiding our cars, calculus plays a pivotal role in shaping our modern world. Consider the smartphone, a marvel of miniaturization and computational power. Calculus is essential for designing the tiny yet powerful processors that drive these devices, optimizing their performance and energy efficiency. It's also crucial for developing the algorithms that compress and transmit data, allowing us to stream videos, share photos, and connect with people around the world. Or take a look at the Global Positioning System, or GPS, a network of satellites that provides location and time information to billions of users worldwide. Calculus is at the heart of GPS technology, enabling us to pinpoint our location with remarkable accuracy. It's used to calculate the distances between satellites and receivers, to correct for errors caused by atmospheric distortion, and to synchronize the clocks of these incredibly precise timekeeping devices. From medical imaging to artificial intelligence, calculus is an indispensable tool for driving innovation and shaping the future of technology. It's the language of progress, a testament to the power of mathematics to transform our world. Calculus isn't just about numbers, it's how we predict and innovate. From forecasting weather to tracking disease outbreaks, calculus helps us anticipate challenges and make informed decisions. Whether it's climate, finance, or health, calculus is the language of anticipation, illuminating the path to our future. In a world of limited resources and unlimited possibilities, the art of optimization, of finding the best possible solution to a problem, is paramount. And it's calculus that provides us with the tools to navigate this landscape of choices, to maximize efficiency, minimize costs, and achieve optimal outcomes. Imagine you're an engineer designing a new type of airplane. You want it to be as fuel efficient as possible, but you also need it to be lightweight and strong. Calculus provides you with the tools to optimize the design, to find the perfect balance between these competing factors. Or, consider a business owner trying to determine the optimal price for a product. Calculus can help them analyze market demand, production costs, and competitor pricing to find the price point that maximizes profits. From manufacturing processes to financial investments, calculus empowers us to make informed decisions that lead to optimal outcomes. Calculus provides a systematic approach to optimization, allowing us to navigate complex systems, identify critical points, and make informed decisions that lead to the best possible solutions. From diagnosing diseases to developing life-saving treatments, calculus plays a vital role in advancing healthcare and improving human health. It's the silent partner of medical professionals, providing the mathematical foundation for medical imaging, drug delivery systems, and disease modeling. Consider the field of medical imaging, where techniques like X-rays, kinetic scans, and MRI scans allow us to peer inside the human body without invasive procedures. Calculus is essential for reconstructing images from these scans, allowing doctors to visualize internal structures, identify abnormalities, and make accurate diagnoses. Calculus is also crucial for developing effective drug delivery systems. By modeling the absorption, distribution, metabolism, and excretion of drugs in the body, pharmaceutical scientists can use calculus to optimize drug dosages, minimize side effects, and ensure that medications reach their targets effectively. From analyzing the electrical activity of the heart to modeling the spread of cancer cells, calculus provides medical researchers with the tools to understand complex biological processes, develop innovative treatments, and improve human health. The world of finance may seem distant from calculus, but math is at its core. Calculus helps model markets, manage risk, and guide financial decisions. Analysts use calculus to track trends, assess risk and return, and develop strategies to maximize profits. It's also key for pricing complex derivatives and managing portfolios in a fast-moving market. In today's data-driven world, we're constantly bombarded with information from a multitude of sources. Making sense of this deluge of data, extracting meaningful insights, and using it to make informed decisions is a daunting task. And it's calculus that provides the mathematical foundation for data science, enabling us to navigate this sea of information and uncover hidden patterns and trends. Imagine yourself standing at the edge of a vast ocean of data, waves of information crashing around you. Calculus is the ship that allows us to navigate this sea, to chart its depths, and to discover its hidden treasures. Data scientists use calculus to develop algorithms for machine learning, a powerful tool that enables computers to learn from data without explicit programming. These algorithms are used for a wide range of applications, from image recognition and natural language processing to fraud detection and personalized recommendations. Calculus is also essential for developing statistical models that allow us to analyze data, identify trends, and make predictions. These models are used in various fields, from healthcare and finance to marketing and social sciences, helping us to understand complex phenomena, make informed decisions, and shape our world. As we've explored in this act, calculus is far more than just a branch of mathematics confined to textbooks and classrooms. It's a universal language that permeates our world, from the tiniest atom to the largest galaxy, from the natural rhythms of life to the complexities of human endeavors. Calculus is the language of change, of motion, and of relationships. It allows us to describe the world around us with precision, to analyze its complexities, and to make predictions about its future. It's a powerful tool for understanding the universe and our place within it. Whether you're a student, a professional, or simply a curious individual, I encourage you to embrace the power of calculus. Explore its concepts, delve into its applications, and discover the beauty and elegance that it reveals in our world. Calculus is not just a subject to be learned, but a lens through which to view and appreciate the wonders of our universe. Ready to unlock the secrets of calculus memory mastery? Let's face it, sometimes those formulas and concepts can feel like a jumbled mess in your mind. But fear not, intrepid learner. Mnemonics, those clever memory aids, are here to save the day, turning calculus conundrums into easily recalled rhymes and phrases. Remember the power rule, that cornerstone of differentiation. It states that the derivative of x to the n is n times x to the n minus 1. To keep this rule front and center in your mental filing cabinet, try this catchy phrase: bring down the power, subtract 1 from the tower. And what about the quotient rule, that multi-step process for finding the derivative of a fraction? Here's a mnemonic to keep it straight. Low d high minus high d low, all over low squared, you know? It might sound a bit silly, but trust me, it works. The key to effective mnemonics is to make them personal and memorable. So get creative. Come up with your own rhymes, songs, or even dances that help you remember those tricky calculus concepts. The more senses you engage, the stronger the memory will be. Section 2. Taming the Calculus Beast. Practice makes perfect and fun helps too. Let's face it, conquering calculus requires more than just memorizing formulas. It's like learning to ride a bike. You can read all the instructions in the world, but until you hop on and start pedaling, you won't truly get it. Practice is the key to mastering calculus, but who says it has to be boring? Think of calculus problems as puzzles waiting to be solved, each one a challenge to test your understanding and sharpen your skills. Start with the basics, like finding derivatives of simple functions. Then gradually work your way up to more complex problems. Don't be afraid to make mistakes. That's how we learn and grow. And here's a secret: calculus can be fun. Look for real-world applications that pique your interest, like calculating the trajectory of a basketball shot or modeling the growth of a population. There are countless online resources, games, and even calculus-themed comics that can make learning engaging and enjoyable. Remember, the more you practice, the more comfortable and confident you'll become with calculus. So, grab your pencil, find a comfy spot, and let the calculus adventures begin. Section 3. visualizing the invisible graphs as your calculus compass. Calculus can sometimes feel like navigating a dark forest with abstract concepts and equations lurking around every corner. But fear not, intrepid explorer. Graphs are your trusty compass, illuminating the path and revealing the hidden connections between calculus concepts. Think of a graph as a visual representation of a function, a roadmap that shows you how the function behaves at every point. The slope of the graph represents the derivative, the rate of change of the function, while the area under the curve represents the integral, the accumulated effect of those changes. When you're grappling with a calculus problem, sketch a graph. It doesn't have to be a work of art, just a quick visual aid to help you see what's going on. Graphs can help you understand the relationship between a function and its derivative, to visualize the concept of limits, and to make sense of those tricky optimization problems. Remember, a picture is worth 1,000 equations. So, embrace the power of graphs and let them guide you through the fascinating world of calculus. Section 4. Calculus in Everyday Life. Finding connections to cement your understanding. Calculus might seem like a distant land of abstract theories and complex formulas, but in reality, it's all around us, quietly shaping our everyday lives. From the way your car accelerates to the design of your smartphone, calculus is the silent architect behind countless aspects of our modern world. So, how can you use this to your advantage when learning calculus? By actively seeking out those real-world connections, you can transform abstract concepts into tangible ideas, making calculus more relevant, engaging, and easier to remember. Next time you're stuck on a calculus problem, take a break and look around you. Can you find any examples of rates of change, accumulation, or optimization? Maybe it's the way the traffic flow changes throughout the day, the amount of water flowing from your faucet, or the design of a suspension bridge. By recognizing these connections, you'll not only deepen your understanding of calculus, but also gain a newfound appreciation for its elegance and pervasiveness in our world. Calculus isn't just a subject to be studied, it's a lens through which to view and understand the intricate workings of our universe. Section 5. You've got this. Building confidence, one calculus concept at a time. Learning calculus is a journey, not a race. There will be moments of frustration, times when you feel lost in a sea of equations, but remember this. Everyone struggles at some point, and it's those struggles that make our triumphs all the sweeter. Building confidence in calculus is like building a house, brick by brick, concept by concept. Start with a strong foundation, mastering the basics of algebra and trigonometry. Then, as you progress through calculus, celebrate your successes, no matter how small they might seem. Don't be afraid to ask for help when you need it. Your teachers, classmates, friends, and even online resources are there to support you. Remember, you're not alone on this journey. Most importantly, believe in yourself. You have the capacity to understand and master calculus. Embrace the challenge, stay curious, and never give up on your pursuit of mathematical knowledge. The world of calculus awaits, and with persistence and a positive attitude, you can conquer it. Section 1. Calculus, a journey of discovery and empowerment. Congratulations, intrepid learner. You've reached the summit of our calculus adventure, having scaled the heights of derivatives and integrals, explored their real-world applications, and armed yourself with tips and tricks for continued success. Take a moment to appreciate how far you've come, for you've accomplished something truly remarkable. Remember that feeling of uncertainty, perhaps even a touch of fear, when you first embarked on this journey? Now look at you. You can decipher the language of change, unlock the secrets of accumulation, and see the world through the elegant lens of calculus. This isn't just about memorizing formulas, it's about expanding your mental horizons, sharpening your analytical skills, and developing a deeper understanding of the intricate workings of our universe. The beauty of calculus lies not just in its ability to solve complex problems, but also in its power to empower us as thinkers, innovators, and problem solvers. With your newfound calculus skills, you're equipped to tackle challenges in fields as diverse as science, technology, engineering, medicine, economics, and beyond. The possibilities are as limitless as the concept of infinity itself. It's easy to feel intimidated by calculus, to perceive it as a daunting subject reserved for math whizzes and academic elites. But as we've discovered together, calculus is far more than just a collection of abstract formulas and complex theorems. It's a vibrant, dynamic field that unlocks the secrets of change, reveals the beauty of patterns, and empowers us to understand and shape the world around us. The key to conquering calculus, as you've experienced firsthand, lies in shifting your perspective from fear to fascination. It's about embracing the challenge, approaching each concept with curiosity and a willingness to explore. Remember those aha moments when a particularly tricky concept suddenly clicked? Those moments of clarity, those bursts of understanding, are the rewards for your persistence and dedication. As you continue your journey beyond this guide, carry that sense of wonder with you. Look for calculus in everyday life, from the graceful arc of a thrown ball to the intricate design of a spider's web. The more you engage with calculus, the more you'll appreciate its elegance, its power, and its profound impact on our world. In an increasingly competitive world, where innovation drives progress and problem-solving skills are highly sought after, a solid foundation in calculus provides a distinct advantage. It's a testament to your ability to think critically, analyze complex systems, and find creative solutions to challenging problems. Whether you're pursuing a career in STEM fields, exploring the intricacies of economics and finance, or simply seeking to expand your intellectual horizons, calculus opens doors to a wider range of opportunities. It's a valuable asset on your resume, a testament to your dedication to learning and your ability to grasp complex concepts. But the true advantage of calculus extends far beyond career prospects. It's about developing a lifelong love of learning, a curiosity about the world, and the confidence to tackle new challenges head-on. The problem-solving skills you've honed through calculus will serve you well in all aspects of your life, empowering you to approach challenges with a clear mind, a strategic approach, and a determination to succeed. As you reach the end of this guide, remember that your journey with calculus is far from over. Consider this your launch pad, your springboard into the vast and exciting world of mathematics and its countless applications. There are always new concepts to explore, new challenges to conquer, and new discoveries to be made. Delve deeper into the branches of calculus, exploring topics like multivariable calculus, differential equations, and vector calculus. These advanced fields offer even more powerful tools for understanding and modeling complex systems, from fluid dynamics and electromagnetism to quantum mechanics and general relativity. Don't be afraid to venture beyond the traditional boundaries of calculus. Explore its connections to other fields like physics, computer science, economics, and biology. Discover how calculus is used to model the spread of diseases, predict financial markets, design safer cars, and even create breathtaking works of art. The world of mathematics is vast and endlessly fascinating. Embrace the joy of lifelong learning, and let your curiosity guide you on an adventure of discovery that will last a lifetime. As we bid farewell to this calculus adventure, remember this: you are not just a student of calculus, you are a calculus conqueror. You've faced the challenges, embraced the concepts, and emerged victorious. Carry that sense of accomplishment with you, for you've achieved something truly remarkable. The knowledge and skills you've gained will serve you well in all your future endeavors, opening doors to new possibilities and empowering you to make a meaningful impact on the world. Embrace the power of calculus and let it be your guide as you navigate the complexities of our ever-changing world. And remember, the journey of learning never truly ends. Stay curious, keep exploring, and never lose your sense of wonder. The world is full of mathematical marvels waiting to be discovered, and with your newfound calculus skills, you're well equipped to embark on a lifetime of learning and exploration. Congratulations, Calculus Conqueror, the adventure